Pleasure to introduce Julien Dubedat from Columbia University, who will talk about stochastic Ricci flow on surfaces.
Thanks, Cedric, and thanks the organizers for inviting me to speak here. So this is joint work with Ocean, who's currently at Columbia, and we're starting with something this fall. So first I'm going to try to motivate what we are trying to do, and then more modestly what we actually do. So the Ricci flow is important geometric flow. So you start from some smooth surface, and on that surface you give yourself an initial metric and start evolving this metric in time. And the evolution of this metric is its time derivative is given by its Ricci curvature. So I'm going to write things in coordinates a bit later on. So for now, what's good to know is that the Ricci curvature is a local invariant, which means that it's something which is computed for the metric in a way which is independent of coordinates. So if you try to get some canonical evolution of the metric, you want the time derivative of the metric to be something that you compute independently of coordinates, and you can make these small modifications. Classical question in Riemannian geometry is to classify these local invariants. So it's understood how you can get all of them. And if you want something which is elliptic, that's basically the only elliptic evolution you can get. And then by very simple transformations, you can replace a by 2 or a squared by 2, and you can get rid of b. So that's basically our basic evolution. On surfaces, it's much, so this makes sense in any dimension. On surfaces, it's explicit and quite simple. So if we give ourselves a flat metric, or at least in coordinates in some patch, we can get something which is flat in that patch. And we write the metric G as some conformal factor E2 phi times this basic metric. Then in this case, the Ricci curvature is actually proportional to the metric, which means that we are always going to stay in the same conformal class. So the conformal class is not going to change, we're just going to change this conformal factor. And if you write things in terms of this conformal factor, you have this nonlinear elliptic equation. So dt phi is E minus 2 phi Laplacian phi, which is minus the Gauss curvature. And again, up to simple transformation, we can adjust this factor b, which we can put a constant there, and if we adjust the constant by putting the mean curvature, then the metric, the evolution has always the same volume. So gt at all time has the same total volume, so it doesn't collapse or blows up. And then it's going to converge to the constant curvature metric. So we're going to flow along the conformal class to the uniformizing metric with the same volume. So that's a nice object. So now I'm going to do finite dimensional things, so just for analogy purposes. So in finite dimension, basic OD, or basic type of OD, is just a gradient flow. So on RD, I give myself a potential, let's say some convex potential with a minimum. Gradient flow for that potential is just you flow along negative the gradient. So that's a deterministic evolution, and the natural stochastic version of that is the Langevin version, where I start with my OD, so my gradient flow, and then I'm going to put a small isotropic noise. So sigma dBt is, so B is the standard Brownian motion on RD. So this is defined by the metric structure of RD, or the Euclidean structure of RD. And this, okay, so this has a generator like that, and an invariant measure like this. And this, you can make this story on any Riemannian manifold. So you give yourself a Riemannian manifold with some potential. So potential is just a function of that manifold. So imagine that it has some unique minimizer. So gradient flow is well defined. So dxt, it's a tangent vector, and the metric allows you to identify tangent vectors with one form. So that's the gradient. So this is something which is well defined if you have a Euclidean structure on tangent spaces. And you can also play the same game where you're going to have your deterministic evolution, and then at each time you're going to put a small random kick which is going to be isotropic in the tangent space. And because you have a Riemannian manifold, it makes sense to have some isotropic noise in this tangent space, which is going to be your small noise unit. So I don't want to write SDs on manifold, so you can do that, but the generator is very simple. So this is Laplace Beltrami minus, this thing. So this dot product is also with respect to the Riemannian structure, and the invariant measure is just your volume measure, and then you put your potential in. So all of these are very natural, and historically like the first type of SDs. That were looked at, even proto-stochastic calculus. So now I'm going to start describing a potential, and then I'm going to try to wrap it up. So if you have again any compact, let's say compact Riemannian manifold, actually G, there's a nice spectral invariant which is determinant of the Laplacian. And how it's computed doesn't really matter to us. So the only thing we need to know is that it's a number that you can compute from this data. So to each Riemannian manifold, you get a number, and this is computed invariantly just in terms of the Riemannian manifold. And this has a simple formula when you vary the Riemannian metric within a conformal class. So you just replace G0 by some locally proportional metric E2 phi G0, and the variation of this thing, which is the only thing we care of, is given by that formula. So to first order, if you have a small perturbation, then you can just write first order variation of this, and you get some formula like that. So K0 is your Gauss curvature. And the way you prove this is you just prove that, and then you integrate to get the overlay. So that's what we're going to use. So now what we're going to try to look at is some formal infinite dimensional manifold. So there's some underlying surface, so that's just a surface, two-dimensional. Riemann surface, so it has a complex structure, and on that surface I'm going to look at all Riemannian metrics which are compatible with this complex structure. So I can as well fix some G0, and then all my Riemannian metrics are all metrics which I can write as E2 phi G0. So my space of Riemannian metrics is just the same as conformal factors once I fix G0. So now, so that's basically trivial. So that's basically flat space. But now what we're going to do is try to get a natural Riemannian structure on that guy. So this is some formal infinite dimensional thing. So what's a tangent vector? So I'm starting from some metric G. I'm going to perturb this metric by delta G within the same conformal class. So this G plus delta G is just G which I multiply by something which is E something small. And I want to, so this is my tangent vector, so this is my tangent vector, which I identify with that guy. And I want to give a norm to this tangent vector. And I want to define this norm in some way which is intrinsic, which depends only on G, which is my point in my space of Riemannian metrics. And basically the only way to do that is to use the L2 metric with respect to the volume measure for G. So this thing, which I think has infinitesimal deformation of G, so I identify delta phi with some infinitesimal deformation of G. How large is this infinitesimal deformation? I'm going to measure its size with respect to this intrinsic L2 metric. So that everything is defined in a way which is coordinate free and free of any choices. Okay, so now I'm going to look at so I've got this M, which is some sort of infinite dimensional Riemannian manifold, and I'm going to define the potential V on that space, so just a function on that space. And this function is up to some not terribly important modifications, log delta of Laplacian. And again, the only thing we need to know is that these things we define just in terms of G, and M is a space of G's which are compatible to some given complex structure. And what we wrote before, so this bottom line, Polyakov anomaly, we can recast it by saying that if I vary G by delta G, then this potential is going to change by that quantity. And this quantity, so K0 dA0 is the same as Kg dAg. So I'm integrating K, which is the Gauss curvature, against delta phi, and then I'm putting some additional correction there. So we have this picture of some formal manifold, some potential, some formal metric, and the Ricci flow is where dt of g is minus gradient of this potential with respect to this metric. And this is a wide-node point of view, which goes back to, I think, Osgood's, Phillips, and Sarnak, that we can think of this flow at top level as some infinite dimensional evolution, which is governed by a gradient flow with these elements. It's also known in higher dimension, it's much more involved, but you can think of the Ricci flow as a gradient flow, and that's part of, Perelman's famous contribution to the Ricci flow to show that there's some similar story in higher dimension. Okay, so where do we stand now? So we have, in finite dimension, given the data of some bona fide Riemannian manifold and potential, we have some natural ODE and some natural SDE, which corresponds to it. And now we have not so bad, formal infinite dimensional Riemannian manifold equipped with a potential. The gradient flow for that potential is the Ricci flow. And now what we're trying to do is complete this. So what is the Langevin flow which corresponds to that? So basically, to get this Langevin flow, what do we need? So we need to start from our gradient flow, and then at each time we are going to add a small random kick, and this kick is going to be isotropic in my tangent space. And now for all these things to work intrinsically, my tangent space is isometric to this L2 dAg. So again, this is on my base space, so my surface sigma. If I look at fields on my surface sigma, I identify these fields with deformation of my matrix, just by varying the potential. Okay. Okay, so then, if everything is smooth, you can work out what are the rules. So, what's isotropic Gaussian variable in some L2 space? This is just white noise with respect to this L2 space. And provided this is a reasonable radon measure, there's no problem in considering white noise, which may be, outside of this space, but this is a well-understood object. So if I denote by psi0 my basic white noise with respect to some basic measure, let's say I start from a torus with flat metric, I'm looking just at ordinary white noise, then the scaling is pretty easy to figure out. So if you go from G0 to G, if you start with psi0, which is white noise for G0, then the white noise for G is going to be E minus phi psi0. So if phi is smooth. So just definition choosing, you get this, and basically at this point, that's what we want to do. So in terms of the conformal factor, we have this part, which is just Ricci flow. So this is my gradient flow, and then I'm going to put a small kick, isotropic, small kick with respect to that precise metric. Okay, so nothing here really makes sense, but so there are some like bad news and some good news. So bad news is if we do like very quick kind of reality check. So if we start from something small, so let's say we're trying to do some like small phi expansion, we're going to replace like the kind of like nasty nonlinear things by 1. So if we forget about these things which are really the troublesome stuff, we just get Laplacian phi minus lambda plus psi0, and this is a stochastic heat equation. So that's a linear SPD, which is very well understood, and we also know completely well the solution of this. So if I just replace this by 1, I get stochastic heat equation. The solutions of this stochastic heat equation in space are Gaussian free fields. So if I fix if I'm looking at space, I've got something which is defined on my underlying surface, it's going to be basically a free field on that surface. And then once we know that phi is typically a free field, if we put it back there, then we see that we have like big issues, because so this doesn't look too good, because we have something in negative regularity, something even more negative regularity, and this white noise is also in negative regularity. This is also in even more negative regularity, so this is kind of it-behaved. Okay, so now slight good news is the following. So if I start from phi, which is smooth, so any smooth function, and I'm going to freeze these two guys at their initial values. So this is some smooth function times adaptation plus some smooth functions times white noise. And I'm going to freeze these guys. Then I've got a family of linear SPDs. So if I freeze these guys, these are all linear SPDs. And because the Dirac energy is conformally invariant, it's actually not very hard to see that all these SPDs have the same invariant measure. So if phi is frozen on smooth, I always get the same invariant measure, which is a GFF whose coupling constant is, in terms of this sigma intensity parameter. So if that guy was smooth, or any smooth function, then, I always be in the regularity class of GFF. So and that's kind of encouraging. So now what we want to do is try to make sense of this equation, at least in some weak sense. Okay, so we're going to again pretend that everything is smooth and write it in terms of the area measure. So look at the evolution of the area measure. So it's going to evolve like that. So again, this is my deterministic flow, and then I've got this additional cake, which is not defined in any reasonable sense. So now we're going to test this weakly. So because A is some evolving measure on my surface, I'm going to test it against some smooth function. I'm going to project my process on a one-dimensional marginal. So how should this guy evolve? So this drift is going to give me that thing. Okay, so that's not so bad. And then the way we understand this white noise with respect to this evolving measure is that once I integrate against f, my diffusion coefficient should be the integral of f squared against the AG. So AG evolves in time. So I've got a time evolving measure on my surface. And along this time evolving measure, my prescription is that if I project it like this on one-dimensional marginal by integrating against the test function, I want my diffusion coefficients to be like that. And now this actually starts making sense, right? So at least now I've got a question which makes sense, which is that I want to construct a joint process on fields phi t and area measures at. And if we want, this guy to be a free field, then, it's well understood that the way to understand this area measure is as a Gaussian multiplicative chaos. So I want a process on fields and jointly chaoses such that at each time, or at least at each fixed time, AT is a GMC for phi t. So now, standard regularization of that guy. And once we have a regularization of AG, then this makes sense. So we want that when we evolve this GMC and this phi, then when I project against f, I get a semi-martingale whose drift is given by that guy and whose diffusion coefficient is given by this. So this is integral of f squared against my GMC measure. So now, that question at least makes sense to construct this process. And that basically, our interpretation of that, Higgs-defined object is by means of this projection. And now this is a well-defined question. Okay, so in case of emergency break the glass of the Dirac form. So I'm going again to go back to some general things, but try to explain what's going on. So if we start from some Markov process on fairly general state space X, okay, so let's say we have a semi-group and generator. So generator has some domain, and we have also a measure M on X, and we're going to ask symmetry or detailed balance, which is that the generator PT is symmetric with respect to L2 D. So again, in terms of Markov chain, this is just detailed balance. And once you have that, you get very powerful tools you can use. So formalism of Dirac form. So in this case, the Dirac form will be take some test functions f which are defined on your state space, which are regular enough that you can apply the generator to these guys. And then the Dirichlet form is going to be a positive semi-definite quadratic form defined on these functions, which, if you have a process, you can write in that way. So there's some domain which is in general hard to understand, but some domain of functions for which this quantity is finite, which is in L2 of M. And now, not every quadratic form which is defined on some domain of L2 can come from a process. And we see this immediately because if G is a C1 function from R to R with derivative less than 1, if we compose f with G, this guy is going to become smaller. So this f of x0 minus f of xt, if we compose with G, is going to become smaller. So certainly, this quadratic form has to satisfy this property. So that's the Markovian property of quadratic forms. And there's general machinery developed starting from the 70s with Fukushima that goes in the other direction. So you start from some reasonable state space, so initially locally compact state space. You give yourself a quadratic form which is defined on some subdomain of L2 of M. And then you ask basically this condition. So that's some main qualitative condition. And then there's a bunch of technical conditions that you need to do something at some point, so which goes under regularity. And then the way it goes is that from a quadratic form you use by essentially Riesz representation, you get a generator which is going to be defined on some dense subdomain of L2. Then you exponentiate this to a semigroup going through first a resolvent, and once you have a semigroup you construct a Markov process. So this is essentially a functional analytic line of argument. And this is a very robust kind of process, so there are many examples starting. In particular, from the Japanese school, defining diffusions on fractals, such as Sierpinski gaskets, more recently work by Sturm on metric spaces, and on state spaces which are kind of complicated or hard to describe or hard to work with, that's some option you have. So locally compact is kind of restrictive. It's been extended to non-locally compact state spaces such as Barr spaces or Lucene spaces, so by Mann-Rockner. And this gives access to things such as dynamical 542, which I'm going maybe to mention again later. Okay, so to kind of contrast and maybe explain a bit how the machinery goes. So again, if we look at a very simple example of RB, so something we understand well. So if I start to write an elliptic generator like this with Aij continuous, basically, okay, so if Aij is very nice, like Lipschitz, then we can go through SDEs and construct solutions. If the Aij are continuous, by working a bit more and along the Struck-Varadhan line of argument, starting from the martingale problem, we can construct processes, so really laws on path space. And once we have laws on path space, we can extract a semigroup of operators. So the martingale problem goes in a bit different way. So we're going to look at symmetric generators. So div A grad, so A is a matrix, symmetric positive or positive definite matrix. So this guy has built-in symmetry with respect to Lebesgue measure. So this guy, I don't need to know anything about invariant measures. This guy has built-in symmetry with respect to Lebesgue measure. What we get is that we can apply machinery of Dirichlet forms with less regularity. So in this case, we can go to H1 lock. And the way Sobolev embeddings go, in dimension 2 and higher, H1 lock is not necessarily continuous. Okay. Again, on regularity at the expense of having to know what the invariant or symmetrizing measure is. And then the way it goes, again, we start from the Dirichlet form, which is just a quadratic form on test functions. From that, we exponentiate to a semigroup, and from the semigroup, you construct a law on the process. Okay, so now I'm going to try to do this in this setup. So first, I'm going to switch a few things under the rug by working on the unit torus. Any flat torus would be exactly the same thing. So on the unit torus, my reference metric will just be standard flat metric. And now I want to do this stochastic Ricci flow on this unit torus. I'm going to evolve the conformal factor, phi of t. So again, what I really want is a joint process where I'm evolving a field and a measure in such a way that at fixed time, the measure is the GMC corresponding to that field, and if I test it against the test function, I get this dynamic. So now this is just one-dimensional semi-martingale, and I want this one-dimensional semi-martingale to have the correct decomposition. Okay, so if I do this for any f, I can do it for f plus g, f minus g, and so on. So I can work out the bracket or cross variation of these two guys on this cross variation. At time dt is the L2 product of f and g with respect to the GMC measure, which I have at time t. So that's what I want. So first so we're going to try to build a Dirichlet form. So first we're going to give ourselves test function. And the way this is set up, what's convenient is to test against the measure. And by very sticky shape it soon, we know that actually if we can go from phi to a at time t by a GMC map, then we can go back also from a to phi at time t almost surely. So we can as well write everything in terms of the measure. So I'm going to give myself a certain number of test functions, h, a smooth function of k variable. So these are functions which are my test function on my state space. So my state space is this kind of complicated space, but then I can choose a class of smooth functions. I want this class to be some algebra function. I can multiply them together, add them together. I'm going to stay in this class, and I can compute stuff together. And because we know what we want the martingale elements of these guys or semi-martingale elements of these guys to be, we can work out what the generator is supposed to be if we apply it to this test function. So that's the generator we are shooting for. And I can, if I want, I can define this class of test function, and I'm defining a differential operator on this class of test function. Okay, and this is defined almost everywhere. Okay, so everything is almost everywhere with respect to certain Gaussian measure. So intensity of the Gaussian measure is going to be determined by this parameter, and almost surely or almost everywhere along this Gaussian measure, if phi and a are related by this almost sure relation, then these coefficients are defined almost surely by each other. So this generator, makes sense. And now we just need to come up with a symmetrizing measure, and we don't have to guess too much. So we're going to take a Gaussian measure. So this is a GFF measure. So that's just GFF measure with some parameter in front. And then we're going to put this Ockron interaction, which is just the UV volume of the measure. So total volume of the torus under this particular GMC. Okay, so I'm writing it as a path integral, but it's well understood how to make sense of all of this. So there's no in the subcritical S. And now, Schwarz pointed out, all we need ever is integration by parts. So here, integration by parts, if lambda is 0, this is just a Gaussian measure. So integration by parts is, I'm taking a functional defined on this space of fields. I'm taking the Frechet derivative in the direction f, integrating it against my Gaussian measure, and this is same as h times an element in my Gaussian space. So just a projection of my field on one function. So this, when lambda is equal to 0, is just integration by part for the GFF measure. And then if lambda is not 0, I just have a potential in front of my measure, and this is the gradient of that potential. Again, everything is computed in terms of the UV measure at that particular point. So that's the formula integrating by part on that space. Okay. So now, so I'm going to make a small detour by many other ingredients. So if again, let's look at this space and put lambda is equal to 0, everything is Gaussian. So this is very standard theory. So I have Frechet derivatives, so I'm taking f, which is a functional on that space. I've got little f, which is a smooth direction, or maybe a Cameron-Martin direction, or just for what we're doing, a smooth direction is fine. And if I differentiate this functional in that direction, I can represent this as some vector, so that's my gradient, dot product with f. So in Maniama calculus, you just fix your Hilbert space. So in this case, this will be the L2 space for the flat measure. I'm looking at functionals defined on the space of fields. And the Maniama gradient for that functional f is characterized by this expression. So if I take the dot product of my gradient with my direction, I get the Frechet derivative in that direction. Okay? So that's actually not what we are going to do. So we are going to do the same story, but we are going to compute everything with respect to the only intrinsic measure we have, which is the Liouville measure. So that one point in my evolution, I've got one measure I can use, which is a Liouville measure, and we're going to do the same thing. So we're going to look at the Frechet derivative of a test function in a smooth direction, and we're going to write it as a dot product of a gradient with the direction with respect to my tangent space, my canonical tangent space at that relevant field. So if we work out what we have for this test functional, things are set up nicely, and we have like very simple expression for the gradient. Okay, so now what did we have? So we wrote a generator. We wrote down the generator we want, and then we made some like educated guess on the symmetrizing measure. And then we have integration by parts. So integration by parts is this integration by parts formula, which has all the information we need about our measure with this correction. So lambda is just this potential correction. And if we perform this integration by parts, we're going to see that this thing is this very nice grad phi square form. So the only thing is that we need to understand grad as this basically gradient with respect to this intrinsic Liouville measure and integrate against the relevant Ekron measure. And now what we have is a well-defined Dirichlet form. So we have a class of test functions. We have a quadratic form defined on this class of test functions. And then this quadratic form is, immediately we see that this quadratic form is Markovian because we have this expression, grad phi square. So if we replace big F by little g composition with big F, where little g is a contraction, this is certainly going to go down just by the chain rule. So we see immediately that this is a Markovian form, and then there's some more going into, checking regularity and stuff. And then if we work on, so there are a couple of ways to go on this, but so if we work on MT square, we can use the weak topology on MT square, and then we're going to be locally compact. So actually, it's not that exotic. And just using this machinery, we are going to get out of it a pair process, which again, the way it goes is that we feed into this machine this Dirichlet form and gives us a semigroup, and then it constructs a process. So we have to do something because the process is defined not for every starting point, which is not surprising, but just quasi everywhere with respect to this measure. So it's a bit better than almost everywhere. And then what we get at the end of this routine is basically what we set up to do is that once we get this process, we know that if we project it on this finite dimensional marginal, then these guys are going to have the correct semi-marginal decomposition. So that answers this first question. Okay, so maybe let me put this. So it's kind of useful to write to compare this with different evolutions that we have. So as mentioned earlier, stochastic heat equation is a basic SPD on the torus here. So Xi0 is spacetime, ordinary spacetime white noise. So the Dirichlet form for this thing is Meliavian gradient correct with respect to the flat measure. So everything is flat, and the 0 means that lambda is equal to 0. So this is just a Gaussian measure. So quadratic potential in the measure, everything linear, we get linear speed. That's the stochastic heat equation. Okay, so there's another fairly natural evolution or class of evolution which was considered recently by Garban, kind of similar to things did by Aaron and Chen. And if you you go back, it's part of a class of SPDs, which was also considered by Albevario and Rockner, in which you have stochastic heat equation plus this term, which is gradient of potential. In this case, the potential is the Coulomb potential. You can do this with a 5-4 potential, you get dynamical 5-4-2. Or you can do this with other types of potential. And if we want to compare things, so in terms of Dirichlet forms, you have this flat Maliavin, or if you flat Maliavin gradient, and you perturb your Gaussian measure by this potential. And that's the dynamic you get out of it. And for what we're doing, we do both, so basically the main thing is we change this flat gradient to some gradient which is intrinsic and adapted to my evolution of measures. Okay. And so now we are going to discuss a bit compact surfaces, so it's not quite let's see. Okay, so compact surfaces is we need to work a bit harder. So again, we can try to play the same game. So we start with Ricci front surfaces. So this is this deterministic part, and then we add this isotropic noise, which is this. Yeah.
Can you just explain where have you used that you were on the torus so far?
Yeah, maybe now it's going to become apart. So I mean, there are things which are swept under the rug. So on the torus, I had a flat metric, and this flat metric has 0 Gaussian curvature. So K0 is a Gaussian curvature of that guy. And then it's going to become clearer why I was sweeping stuff under the rug. So now we can play kind of same game. So we have test functions, a natural class of test functionals on this space. And then we can write, looking at this which doesn't make sense, we can write a generator which makes sense. Okay. If we interpret this in a reasonable way, then that's the generator we want to come out to everything. So these guys are defined with respect to this evolving GMC measure. That's the main point. Okay. So now if we want to define a measure on measure, so we know how to do it by UV theory, so constructed rigorously by David Tupienan, Rode and Vargas. So now it's going to become more salient what the choice of reference measure matters. So for the torus we have this very nice flat reference measure, and then we don't need to think too much about it. So now if we start from a G0, we're going to get a measure on fields, and did I write it? Yeah, so I want my so point is the following. So my chaos A is e to phi dA0. So I've got some dependence on the 0 which is explicit there, and I've got some dependence which is implicit in these columns. So because when I do epsilon modularization, I'm doing it in the metric G0. So there's some additional dependence on the metric which is hidden in the epsilon regularization procedure. And this is going to throw us off by this factor. So you have this correction, which is well known and well understood in UV theory. That's what you need to put to get something, which in the end is not going to depend on the choice of G0. So for a G0, I've got a law on phi, and then I'm going to push it forward by this map, which depends on G0. If I change G0 to some other reference measure, I'm going to get another law on field. I'm going to push it forward by another GMC measure. And then I want to get the same push forward up to multiplicative constant. So we don't care about overall multiplicative constants in front of the measure, so that's just the overall speed of the process, which is not really relevant. So that's what you need to do to have some well-defined, independent of choices measure nu, which is a measure, it's better to write it as a measure on the space of measures. So that's the measure induced on the space of measures on my surface. Right, so this is this point. And then we're going just to, in this case, we're just going to write the Dirichlet form. So Dirichlet form, if we want to write this intrinsic Dirichlet form, we actually don't, we have a choice. So we have nu, which is this sort of canonical measure on GMC measures, so for a given intensity. And then we have this gradient, which is everything is computed with respect to now this measure, so A depends on my integration element, which is implicit. And then again, we just need integration by part, so now integration by part is going to be a bit more complicated because we have these things which are going to come out and so on. But and now, so then that we see that we are kind of like over naive. So so basically, this heuristic was treating. So in the heuristic derivation, we are just treating these measures as actual non-quantum measures. So if you will, with scaling dimension actually 2. But once we put this GMC correction, because of the regularization scheme, so effectively the scaling dimension is going to be adjusted by this this gamma. So this is the actual Duvet gamma. So not being super consistent in notation. So gamma is linked to sigma by something like gamma is sigma over square root pi or something like that. Okay, so we have this correction. So basically, so we have this kind of like naive derivation which doesn't take into account like the correct scaling dimension of these guys. And if we look at this canonical directly forms, then the process which comes out as this dimension correction. So the correction is really this plus gamma square over 4 to what we are trying to do. Okay. Yeah. So conical singularities. So again, mostly from the point of view of UV measure, it's kind of interesting to look at insertions. So if we forget about the noise, you can look at versions of the stochastic Ricci flow with insertions which are going to force your flow to have conical singularities. So if you want to evolve not in the class of smooth metrics, but in the class of metrics which have particular conical singularities or particular points, you can make this modification where you put this forcing on the right-hand side by Dirac masses. And then you can go through a similar routine and you get this UV measure with insertions. So not surprising, okay, so okay, so maybe I'm just going to wrap it up. So well, maybe if I go there, so no, that's way too far. Yeah. So again, so if you look at, okay, so this is a linear partial differential equation. So this is linear PD, and then we put some additive white noise. This is a semi-linear stochastic partial differential equation. It has nonlinearity, but the nonlinearity is not in the leading term in terms of degree. And then it's driven also by ordinary white noise. And this is a fully nonlinear stochastic partial differential equation, because we have nonlinearity, which is also in the top degree. So these things, so again, in this actually class of equation, you can get solution using Dirac form techniques, and this goes back to also Adbadari and Rottner. You can do that for the 5, 4, 2, and so on. But now for these equations, you can ask more precise questions, which are, if you fix your white noise realization, is a solution determined by the white noise realization. So there's a notion of strong solution. There's a fixed point formulation of the solution which uses a parabolic heat kernel, which you can do because you're in a semi-linear setup. And in that case, this noise actually doesn't make any sense. I mean, at face value at least. So what we have is a notion of weak solutions. So kind of direction of question is, can we push forward and have some way to define the noise? You know, in the same way that in the Bismuth mechanical aleatoire, you can define noise on tension spaces of Riemannian manifold just by using stochastic parallel transport. So maybe it's possible to have some way to have a well-defined white noise and then try to decide whether this was the solution. So first question for strong solution is actually try to define the noise, and then we just point around to avoid having to define the noise because at face value it's this. Let's see. Yeah. This thing is, already well defined. It's not, this product is really something you don't want to deal with. And kind of like novelties, I mean, of course, there's been huge developments in SPDs recently, in particular around regularization structure, but mostly for semi-linear SPDs. So it was very important that nonlinearity was not in the leading term because it uses a parabolic in kernel in the analysis in a crucial way. And there are some other methods which can deal with, such as paraproducts, which can deal with full nonlinearity, but in that case, noise is colored and your solutions are basically have classical regularity, and the nonlinearity is classically defined. So in this case, we have kind of worst of both worlds, but we have to kind of find a workaround, and then there's some like improvement in terms of regularity, having continuous evolution, not just of the measure, but also of the underlying field. And that point is not completely clear. So it would be nice to have some approximation scheme. So maybe in the same way that, for instance, in Struct-Varadan, you can construct diffusion by approximating them on small time intervals by Brownian motion with particular diffusion elements, and so on and so forth. So in this picture, you can think of, let me look at this picture, you can think of freezing phi on the small time interval, and maybe freezing it and smoothing it a bit. And then you have a stochastic heat equation, which you can evolve for a small time interval. And then after that, you just read this new value, and then we do this freezing and smoothing. So there's natural somehow approximation scheme, which looks like reasonably should converge to this thing and gives a much more concrete and hands-on construction of the process. But because basically of this, because of this, the way the noise is set up, that looks kind of challenging. And similar idea would be to go in a Wong-Zakai direction, where we have some scheme where we could show that this is the limit of classical smooth solutions of equation with color noise. Okay, so I think that's it.
Is there any sort of natural discretization of this?
Natural, I don't know. I mean, I think you can write. Well, if you want to write a DGFF stuff, you could write. But natural, I don't know. Yeah. But I mean, so.
I meant more with maps, I guess.
Yeah. So the important thing is that this dynamics is within a conformal class. So if you have a natural map dynamic, so this is local dynamics, which preserves locally the complex structure. So if you think of diagonal switching dynamics on maps and so on, my kind of somehow impression or guess is that wouldn't preserve locally the complex structure. So that would have to be some different class of dynamics.
So how is this related to what Christoph does?
I know you are dosing up a good part of it, but so this is the exact. Okay, so there's V0, there's V0, and then now there's no zeros.
But are you certain that there's not a change of variable that will reduce one to the other or something?
No, it's not. Yeah.
But I mean, you started with a measure on conformal classes, on which the volume form is not really defined. Right? The first metric you gave. The first slide, and physicists kind of expect that I don't know where it's written. Physicists expect that it's Liouville field theory.
Yeah, so that's okay. So maybe that's a good point. Yeah. So So this is a very indirect way to define this volume measure on
Yeah, that one.
yeah, so it's a very indirect way to define this canonical volume measure on this, because we define the process, we define the symmetrizing measure, and the symmetrizing measure should be related to the volume measure by this thing, and we know what kind of the action is, because we know what the potential is, so we have these corrections going into, yeah, so this is a roundabout way to define, to go about defining this volume, formal volume measure on that space, yeah, so that, yeah.
Let's thank Jan again.